So we begin our seminar, and our speaker today is Stanislav Speranski from St. Petersburg University and Steklov Mathematical Institute in Moscow, who will speak on negation as a modality in a quantified setting. Please.
Thank you very much for having me. This is going to be an extended version of the talk I gave at Workshop 2019, and also at the workshop on FD-based model logics, also last year. And it can be also viewed as a starting point in the investigation of predicate intuitionistic model logics. Now I'm going to start with some preliminary motivation. Here's a word on intuitionistic negation, which shouldn't be taken too seriously, actually. In predicate intuitionistic logic, proving phi provides a verification of phi, while proving not phi gives us a demonstration that each verification of phi yields a verification of bot. And since bot must not be verified, it implies that phi cannot be verified. So intuitionistic negation behaves as a kind of impossibility operator of a special sort, rather than corresponds directly to falsification. This feature leads to a number of suggestions on how intuitionistic logic may be improved. Here I mentioned two of them, even though I'm going to take a different route. And now, first of all, Kreisel and others criticized trivialization and irrelevance of witnesses under this interpretation, which roughly corresponds to Kleini's realizability. Roughly, the idea is that if phi is not verified at all, then practically anything serves as a verification of not phi. And this motivates modifying BHK semantics appropriately. Those who want to know more about that can take a look at the paper, for instance, Logic of Justification by Artemov from the Review of Symbolic Logic. Here's another suggestion. David Nelson, sorry, not Edward Nelson. David Nelson, former student of Heiting, he suggested that we should add strong negation which corresponds directly to falsification. So this leads to a modification of Kleini's realizability semantics where you have positive and negative realizations. And this is something I particularly like because if you're trying to constructivize game theoretical semantics for classical logic, then the negation you get is exactly strong negation. It's not intuitionistic negation. There are good reasons for that because intuitionistic negation is defined in terms of implication, and it's not clear what is implication from a game theoretical perspective. While strong negation, it switches the roles of verify and falsify, even though now we restrict ourselves to constructive or computable strategies, not to arbitrary strategies. This is all very interesting, but actually this is not something I'm going to talk about. So what I will be concerned with in this talk is Dawson's perspective on negation, something that corresponds to direct falsification. Now, this leads to a number of suggestions on how intuitionistic logic may be improved. I will mention two of them here, but actually I will not be concerned with any of these two suggestions in my talk, but still something should be said about this. Now, first, Kreisel and others criticized trivialization and irrelevance of witnesses under this realizability interpretation, which corresponds to Kleini's realizability interpretation, of course. And this motivates modifying BHK semantics. If you're interested in knowing more about that, you can take a look at Artemov's paper, Logics of Justification, for instance. Roughly, the point is that if phi is not verified at all, then anything, practically anything, would verify not phi, right? Simply because there is no verification of bot. And Another suggestion is by Nelson. So Nelson, who was a student of Heiting, he suggested that we should add strong negation, which corresponds directly to falsification. And this is actually a very interesting approach, something I'm very much interested in. So roughly the point is that now you have positive and negative realizations, and negation switches between the two. So if you will follow Hinticke and try to provide a constructive game theoretical interpretation for first order logic, then you will end up with strong negation actually. So a constructive version of classical negation from a game theoretical perspective would be strong negation, not intuitionistic negation. And this is also because intuitionistic negation is interpreted via intuitionistic implication. It's not clear how to interpret implication in game theoretical terms. Now, this is all interesting, but this is not something I'm going to talk about. I'm going to talk about Costa Dawson's perspective on negation. So he proposed to take seriously the idea that negation can be thought of as a negative modality, or more precisely, a model operator of impossibility. You can already see that in standard possible world semantics for intuitionistic logic, where you have that not phi is true at W if and only if phi is not true at any world accessible from W. Well, accessible means informationally accessible here. So you have a pre-ordering or a partial ordering as usual. However, this will be too strong for our purposes. And this information ordering should be replaced by an accessibility relation which agrees with the information ordering in a suitable way. Now, axiomatically, what it means is that we shall use the contraposition rule. I mean, the weak contraposition rule. So it means that there is no negation above the line, but there is some negation below the line. If phi implies psi, then if psi is impossible, then phi is also impossible, right? But you have a rule like that. So it's a kind of anti-monotonicity rule. Just like in the standard modal logic K, instead of necessitation, you can add something like phi implies psi, then box phi implies box psi, and similarly for diamond. Here you have just one anti-monotonicity rule. It is a rule, not a law. And although trivially admissible in our system, we will just explicitly include it in our system, it will not be derivable. So what it means is that the corresponding implication, which I denote here by CR prime, will not belong to our logic. Furthermore, we shall be interested in local derivability. It means that our logic will be closed under the contraposition rule, but this rule will not be used in derivations from a non-empty set of premises, just like in modal logic. So the only rules that we will have is modus ponens and two Bernoulli's rules, right? Because we're going predicate. Well, what it means is that even Johansson's minimal logic is too strong for our purposes. And the reason is not because we know a lot about bot, but just because minimal logic treats negation of phi as phi implies bot. And what it means is that this rule will always be derivable, or that this law will always be derivable, because you just need to substitute here psi implies bot, and it will become something like transitivity of implication. So unless you're going substructural, you're doomed to have this kind of thing if you interpret negation as phi implies bot. So we don't want to reduce our negation to implication. Now, I'm going to begin by expanding Dawson's propositional logic, which he calls N, which yields the weakest quantified logic we shall be concerned with. Actually, this logic is probably not that much interesting in its own right, but as always with model logic, you start with something as weak as possible. So the reason why we investigate the least normal model logic K is not because we're so much interested in K. Perhaps we're interested in S4 or S5 or GL, but the point is that K provides a common basis, and you can develop some technique and then extend it using the canonical model construction to other logics, whatever your intuition is. Now, our predicate calculus for quantified version of N, that is Qn, it naturally expands the propositional Hilbert type system for N. And it employs the following axiom schemata. So it's just the usual stuff for the most part. So the first two axioms, they're responsible for having the deduction theorem, of course, provided that the only rules you use in derivations are modus ponens and two Bernoulli's rules. So that's the usual stuff. You have the usual axioms for conjunction, the usual axioms for disjunction. You have one more specific axiom, which says that if phi is impossible and psi is impossible, then their disjunction is impossible. It implies that their disjunction is impossible. It is really needed for the canonical model construction to go through. You also have two quantified axioms. You will find them in the standard formulation of predicate classical or intuitionistic logic. So the only thing that we've added so far is this particular axiom. Actually, the other direction of this De Morgan law will be derivable using the contraposition rule. So you have one De Morgan law, essentially. So what we have here is the positive axioms of predicate intuitionistic logic in the extended language, of course, in the language with negation, but our negation is just a negative model operator, plus all instances of N. Then we also employ 4 inference rules. 3 of them are known to everyone, right? So this is just the modus ponens and 2 Bernoulli's rules. And on the top of that, we add exactly one model rule. That's the contraposition rule. So it's our model rule. It will not be used in derivations from a non-empty set of premises. Well, the Bernoulli's rules are as usual. If phi implies psi and x is not free in phi, then you can generalize and get phi implies for all x psi. Well, and similarly for the existential quantifier. So if phi implies psi and you have a parameter x that is not free in phi, not free in psi, then whatever, if you have just some value for that parameter which satisfies the premise, then you have the conclusion. So that's why you have this. So these are the standard rules of predicate intuitionistic logic or predicate classical logic, if you like, plus the contraposition rule and nothing else. Now we denote by Qn the least set of formulas containing the axioms of our calculus and closed under its rules of inference. So that's the usual thing, including the model rule, of course. So we have a logic. Now, given a set gamma of sentences and a formula phi, we write gamma derives phi if and only if phi can be obtained from elements of gamma and theorems of Qn by means of modus ponens and the 2 Bernoulli's rules. So this is a local derivability relation. The model rule is not used here. Well, it can be used, of course, if gamma is empty, but we don't use that. Now, you can go further and you can define a general notion of logic. And by logic is meant simply a collection of formulas closed under the 4 rules above and substitutions. So there are some technical details here missing, Because, well, in order to define substitutions in first order logic, you need to be careful. If you will take a look on how it is actually done in the book, for instance, Quantification in Non-Classical Logic by Gabay, Shechtman, and Skvortsov, you will see that there are quite a lot of details here. But the logics I'm going to be concerned with will be defined explicitly using schemata. So it will always be clear that whatever the notion of substitution is, they will be closed under substitution. So everything is fine.
Stanislav, can I interrupt you for a moment?
Sure.
So could you go back to the list of axioms of logic N? This one, next one, yes, this one. So this axiom N, could you, in a few words, explain what was the motivation for this principle? Why do we want to have it? Because it is valid in K or for some other reason. So what was Dawson's motivation for?
Well, he doesn't explain his motivation, actually. He just says that it's natural to have that because otherwise you will not be able to carry out canonical model construction in a nice way. And it is in fact clear from the construction that there will be problems if you don't have it. You have a lot of problems trying to prove the disjunction property for prime theories. So roughly that will be the case. For us, it will not be that important. At some point, we're going to add all De Morgan laws whatsoever. It's just the minimal thing you need for the construction to go through. So this is a technical thing, essentially. You can try to motivate it by simply reading that if phi and psi are impossible, it should imply that disjunction is impossible. But in order to understand why this is the case, you already need to have a nice semantics where the accessibility relation is somehow connected with the information ordering. Mm-hmm. And the usual property which is taken there, we're going to see that, is that the composition of the information ordering and the accessibility relation is a subset of the accessibility relation. And this thing will always satisfy N. So it will always verify N. This relation, it appears in the work by Lidek and Visser, for instance. So it's, wow, I mean, it's hard to make.
I may remark something, and
Yes.
The other direction follows from the rule. So this really means an equivalence.
Yeah, yeah. Okay. Yeah, so I suppose that if you don't have any disjunction in your language, then this axiom disappears without a trace or something like that.
Well, probably, but the right, but so some of the logics we're going to be concerned with, they also conservatively extend some nice relevant logics like FD, like first degree entailment, where you have conjunction, disjunction, and negation, and they behave in a certain way. Actually, they will satisfy both De Morgan laws and also double negation, introduction, and elimination. So at some point, we will need that anyway.
Okay, go on, yes.
Okay, now, if we have a logic, if we have a Qn extension, a logic that includes already Qn, then we can reduce derivability with respect to L to derivability with respect to just Qn. We just add L to the collection of sentences, and that's all. So everything that we're going to, so what it means roughly is that most results you will prove for Qn, they will generalize to Qn extensions, at least some kind of extension lemma the deduction theorem, and things like that, they will generalize readily. Now, here comes some semantics, but this semantics is not very intuitive. So following Dawson by a frame, we mean a triple, where you have a non-empty set of worlds, you have a pre-ordering, so that's the usual stuff. So this is responsible for how our positive connectives behave, and they behave exactly as in positive intuitionistic logic. But you also have an additional binary relation on W, which satisfies this condition. So when I say composition, I mean that you go from the left to the right. So you first apply that and then apply R. So this is a rather specific condition, but it exactly corresponds to this axiom, this specific axiom N. Now, naturally, one might wish to consider frame conditions which are stronger and more natural than this one. So a good example is this condition. It corresponds to so-called condensed frames in Dawson's works. And this is, for instance, the condition that appears in a recent paper by Liddick and Visser on constructive strict implication. So they use this condition rather than a more general one, because they think that it is more natural, it's nicely motivated, and so on. Now, similarly to predicate intuitionistic logic, we can define extended domain models for a Qn. So what it means is that you have a frame and then you define a collection of domains such that they extend in a certain way. It means that if a world is accessible from a given world, then the domain is the same or larger than the domain you started with. And similarly for the information ordering. So these are Qn models, and it of course leads to the logical consequence relation for Qn, and then you can prove the strong completeness theorem for Qn. So here it is. So all of this, there is nothing new here. So you do that, you just combine a little bit of the strong completeness result for Qk, I mean the quantified version of the least normal logic, non-normal model logic K, and some other features from the proof of the strong completeness result for predicate intuitionistic logic over extended domains. Okay, so this is just the least logic we shall be concerned with.
Stanislav, may I ask you something?
Yep.
Very briefly? Can you go back one slide before we leave this session? So I was wondering, are there like weaker relation between this less or equal and R, such that we can go without?
You mean weaker than this one?
Yes, such that we can go without, because I guess this captures not only the De Morgan stuff, but also the contraposition rule, right?
Well, yeah, as a rule.
Yes.
But we have it, right? So the least condition you need to have, if you want to have both the contraposition rule and that De Morgan law, will be this one.
Okay, but we don't know of a weaker condition such that it doesn't allow for or it doesn't say anything about the De Morgan law and just validates the contraposition rule.
No, I guess not.
Oh, okay, because I was wondering, then one can do like a label calculus and maybe like make a modular thing. But yeah.
So actually, I mean, you can replace frames by condensed frames everywhere. It will turn out that the canonical model will satisfy this condition. Just like in the case of predicate intuitionistic logic, you end up with a partial ordering, not just a pre-ordering.
Okay.
Right. But this is not the minimal condition you might have. And in some
Yes, yes.
generalizations, it's nice to look at that.
Yes, even though I saw this exact same generalization in a recent work in which by Liu and Ciardelli, where they, maybe you can be interested in that, in which they develop conditional logic, intuitionistic conditional logic. So there is a lot of use of this kind of condition, if I'm not wrong.
Okay.
Yeah,
Okay, take a look.
thank you.
Okay, so now I'm going to consider some logics I'm actually interested in, and these logics extend Qn in a certain way. So one of them is called Qn star. So the point is the following. In the course of developing framework for the study of logic programs with negation, Kabbalar, Odintsov, and Peirce introduced the propositional logic n star extending n. And this logic has turned out to be very useful. So when I say logic programs with negation, I mean so-called well-founded semantics for logic programs, or stable models, so-called answer set programming and its modifications. But without going into details, what are the good logical properties of this logic? So first of all, of course, psi implies psi is a formula that is true at all worlds, so it's intuitively top. But not top doesn't behave as bot in our logic. One can check that. Now, in n star, once you add certain additional laws, bot will behave exactly as this formula. And it will lead to the fact that our logic will be a conservative extension of predicate intuitionistic logic. So you have a predicate intuitionistic logic with an additional impossibility operator on the top of it. Second thing is that unlike this strange semantics, logic n star has a very nice and elegant Routley style semantics. So in Routley style semantics, you have a set of worlds, you have an information ordering, and you have exactly one anti-monotone function which is responsible for negation. And the intuition is the following. Not phi is true at a given world if and only if it is not true at a star world. So a star world is just some kind of maximal world. And if you cannot make it true there, then its negation should be true at the world you start with. So this is a very nice semantics, and it has been used extensively in relevant logics. So for instance, if you take a look at some books like What is Negation, edited by Gabay and Vansing, you will find there a paper written by Greg Restall, which is called Negation in Relevant Logics, or How I Learned to Stop Worry and Loved the Routley Star. So that's the official title of the paper. Also, this logic n star is intimately connected with Dawson's view on intuitionistic model logics, as well as Vakarel's classification of negations. So it fits nicely into this system. Now, we're going to bring quantifiers into the picture. So we want to define Qn star. Now, first, I'll just try to add some additional axioms that were added to the logic n, and we'll see what will happen. This will not suffice. I mean, the logic I'm going to end up with will not still will not have a nice Routley style semantics. But then I'll add something more, and it will have a nice Routley style semantics. But there will be some interesting aspects of it. So here are these axioms. So think of phi implies phi as top. So what is said here is that bot, which is not top, implies everything. And that it is not the case that top implies bot. And also you have this additional De Morgan law. Now, the first two axioms actually guarantee that you have a conservative extension of predicate intuitionistic logic. And this axiom is in fact needed if you want to have a nice routely style semantics, but it will not suffice for the quantified version. Now, suppose that I've just added these axioms. So these axioms plus n is n star. Now I denote like this the derivability relation for this logic, and I will modify my collection of frames appropriately. So I will call a frame special if the accessibility relation is serial, and for every world W, the collection of all worlds accessible from W is directed with respect to the information ordering. So this is a rather specific condition, which turns out to be equivalent to some condition on routely style semantics, but it will not work in the quantified case. But for the moment, just let us stick to this condition. So the motivation is as following. A frame is special if and only if the propositional versions of these three axioms hold in each model for n based on the frame W. Now, suppose that by Qn star models, we mean Qn models based on special frames. That's it. Here is the corresponding logical consequence relation. And then we again get the strong completeness result. Now, the good news is that this logic, Qn star, will be a conservative extension of predicate intuitionistic logic. So if we exclude negation, well, our negation is just a model operator, and we'll introduce this bot. So bot is not phi implies phi for a fixed formula phi. Then this fragment is precisely predicate intuitionistic logic. The bad news is that this logic doesn't seem to have a nice routely style semantics. So this thing doesn't seem to be equivalent to a nice routely style semantics, unlike in propositional logic. We need to add something more. And the way we do that is we introduce the logic Qn sharp, which also adds 3 additional axioms. So remember that we have all the De Morgan laws. So let us think of these formulas as generalized De Morgan laws. So for all x not means not exists x, right? So these are our generalized De Morgan laws. We're going to add them, but now we have a problem. And this problem is rather specific for predicate logic. The reason is, if you're going to take a closer look at these axioms, then you will notice that they may be thought of as playing the role of Barkhan's formula. So if these formulas are true, then you will not have extended domain semantics. You will have constant domain semantics with respect to the accessibility relation at least. So, and that somehow forces us to switch to constant domain semantics. But then we also need to have constant domains with respect to the information ordering, and then we add CD. So CD is the axiom schema that is responsible for constant domains in intuitionistic logic. So since we already have that, we also add CD, and with these 3 axioms in place, we may hope that we will get the strong completeness with respect to constant domain models, perhaps based not on some strange special frames, but on routely frames. And this turns out to be the case. So here I say following Kabbalar, Odintsov, and Peirce, but actually following routely. It's just that they modify that a little bit. So a routely frame or a star information frame is just a triple where you have a non-empty set of worlds. You have some pre-ordering on W, right? So this is just a frame for intuitionistic logic. And you also have an anti-monotone function from W to W. It's anti-monotone. It will satisfy the contraposition rule, and it will also, I mean, the whole thing will satisfy all the De Morgan laws. So that's why you must have them, right? If you plug in this anti-monotone function anyway. Now, Routley frames, they're particular cases of special frames, and they are practically equivalent to frames satisfying the property that for every world W, the collection of all accessible worlds has the greatest element with respect to the information ordering. And roughly speaking, this greatest element is your star world. So you just go to that greatest element and try to understand whether phi is true there or not. If it is not true, then at the world you started with the negation is true. So that's your intuition. Now, it doesn't really matter whether you will stick to these special frames or to Routley frames. They're practically equivalent. These look nicer, so I'm going to stick to Routley frames, of course. This may be called star frames, if you like. Now, QN's sharp models are constant domain models. So we have one constant domain, and at each world we see that particular domain, which are based on Routley frames. Now we relativize the logical consequence relation to these models, and we get the strong completeness result. Well, actually not in full generality, but I will say something on that a little bit later. So the point is that I can prove that for at most countable signatures, and there is some problem related to uncountable signatures. I'll say something, a few words on that at the very end of the talk. So that looks very, very strange, but it is the case. And again, it extends conservatively predicate intuitionistic logic. So it extends conservatively predicate intuitionistic logic with a specific model operator, negative model operator, whose behavior is determined by this anti-monotone function. Okay, well, just to make that clear, the reason why we need to have constant domains is the following. So suppose that you say that for all x, not phi. Not phi means that you go to a world accessible from this world and do something, right? And for all x means for all x at this particular world you started with. Now, when you say that not exists x, it means that first you go to a world accessible from it, and then look at something that happens in the domain of that world. So if this world has, if the domain has extended, then you have more individuals in that domain, and the formula may fail. So roughly that's the point, right? So that's what happens in Barkan's formula, where you write something like for all x box, then box for x, and these things should be equivalent, right? So it depends on whether first you go to an accessible world and then look at the domain, or the other way around. If the domain is constant, it doesn't really matter. Okay, so now here comes something interesting. Recently, Hannes Leitgeb advocated a certain system of what he calls hyperintentional logic. So I'm going to let hype and Q-hype be its propositional and quantified version. He has a long story behind that, but I'm going to say I'm going to tell you just a very short story about why this logic is very natural without any real philosophical motivation whatsoever. The reason roughly is because this logic corresponds to the Routley frames as they were originally introduced by Routley. So in Routley's works, these Routley frames are actually, they satisfy double negation introduction and double negation elimination. So they're involutive. And the logic of involutive Routledge frames will be exactly hype. So that's the point, actually. Well, this logic, I mean, at least the propositional version of this logic was not originally introduced by Leitgeb. It was introduced by Moisel. Well, at least I was said that it was introduced by Moisel. I haven't seen the paper. It's very hard to find it. So Hannes has a good excuse for why he haven't seen that paper. But there was only a propositional version of this logic. It was in a paper published in 1942 or something. But then recently it has been observed by Odintsov that hype coincides with the logic obtained from N star by adding the laws of double negation introduction and elimination. And this gives us a very nice Routledge style semantics for hype, which is much simpler than the one suggested by Leitgeb. If you will take a look at the paper by Leitgeb, it's more than 90 pages, and describing its semantics takes like 3 pages or something. I mean, it's a very peculiar semantics, actually. But what do you, well, also, I mean, the reason why it's so peculiar is also because he argues that this is a real hyperintentional logic, right? So you shouldn't have a simple semantics which is already known in non-classical logics, because then everyone will say, well, look, this is an intentional semantics. This is okay. This is not hyperintentional. On the other hand, this is only about the propositional version of hype. But the only application Leitgeb provides for hype in his paper that contains 19 pages is an application to semantic paradoxes. And it requires a quantified version of his logic. Because of course, there you have quantifiers, right? So roughly the story is that he tries to add a nice conditional to Kripke's theory of truth. So that this is just to make a long story short. Now I'm going to provide an alternative axiomatization and semantics for Q hype, and also prove the completeness result, the strong completeness result. So Hannes claims that he has the weak completeness result for Q hype in his paper with respect to his semantics. But the problem is that the proof is only sketched. So it's less than 1 page. And he refers extensively to Gardenford's and Rysowa-Sikorsky for details. At the same time, there are already some mistakes found in his work, for instance, concerning the disjunction property. So it's not clear how easy it is to fill in the details. Now, I'll have a self-contained strong completeness result with respect to an alternative semantics, with respect to Routledge style semantics. And it can be extracted from this result at once. So you just look at the canonical model construction, and you see immediately that if gamma contains the laws of double negation introduction and elimination, then this thing will be strongly complete with respect to models in which Routledge frames are involutive. And you will see that at once. And that's the end of story. So it's just proved in 3 lines from that result. Now, here are some details. Define the logic Qn circle to be Qn, just Qn, right? Not Qn star, not Qn sharp, not something like that, plus the following axiom schemata. So you have double negation introduction and double negation elimination, and nothing more. Now, the first proposition says that the axiom schemata N, something Leff was concerned with, right? I mean, so something that he didn't like. It will be redundant in this system, so it will be derivable in this system. So what it means is that if you have just quantified predicate intuitionistic logic with these two, then N will be provable there. Also, all De Morgan laws will be provable there, and all generalized De Morgan laws will be provable there. So this logic will be an extension of QN sharp. So you will have all those axioms, no matter whether you think that they're special or not, they will be provable in this system. So Q hype is so QN circle is axiomatized by just taking the axioms for predicate positive intuitionistic logic and adding the laws of double negation, elimination, and introduction. And that's all. Well, and here's a simple corollary. Q hype as presented by Leitgeb coincides with QN circle. So that's just the same logic. Well, actually, his axiomatization is not minimal, so he has several redundant schemata and things like that, but you can prove that this is just the same logic. And from now on, I shall use Q hype and QN circle interchangeably. Now, here is the completeness result. So we have a Routley frame, and let us call it involutive if it is involutive. If you apply this star operation twice, you'll get to the same world. And QN circle models are just QN sharp models whose frames are involutive. So that's all. Then relativize everything to the class of QN circle models, and you get the strong completeness result. So in other words, Q hype is strongly complete with respect to the class of all involutive Routley frames. And Routley frames, they were involutive already in the original paper by Routley, because they were concerned with the semantics for first degree entailment, where you have both double negation introduction and double negation elimination, which corresponds to being involutive in the first place. So that's what they had from the very beginning. Okay, and also this logic conserves, that it extends conservatively predicate intuitionistic logic as usual. So originally this result is due to Leitgeb, but it is based on his weak completeness theorem, of course. So here you have an alternative simple proof, well, relatively simple model of what we've proved so far. So all these logics starting with QN star, they are conservative model enrichments of predicate intuitionistic logic. So they're...
When I ask a question again,
yeah, sure.
Is this not with respect to constant domains?
Yes, this is also with respect to constant domains, because...
So it's not really intuitionistic predicate logic, but with...
Oh, yeah. Intuitionistic predicate logic plus CD, right?
Yeah.
Over constant domains, yeah. So here you take QN sharp models, which already have constant domains, and then you require that their frames are involutive. Sorry, yes. So a conservative extension of CD, right?
Also, Stanislav, maybe you can also add comment a little bit on this notion of hyperintentionality that Leitgeb was after, and you are claiming that this semantic somehow shows that it is not very hyper. What is, well, could you explain what do you mean here?
Well, frankly, I don't want to go too much into details because there is already a paper of 40 pages on that.
By whom?
By Odintsov and Vansing.
Okay.
So first, it was assumed that I will be involved, but then they wrote this paper. I've written this quantified paper. So, right. But what I know is that Leitgeb still doesn't agree with them, right? Because what they claim is that his logic is perfectly intentional and give some good reasons for that. But it also depends on how you define intentionality and what you mean by that. So roughly, their argument is that if you, well, it's very roughly, but if you call this logic hyper-intentional, then you will also have to call hyper-intentional many logics which are already available in the literature, which do not respect the replacement rule. So in practically all logics with strong negation, you cannot replace, so you cannot substitute equivalent formulas instead of each other. So what you need is that phi is equivalent to psi, and their strong negations are also equivalent. Only then you can replace them in any context. Otherwise, you can only replace one of them by the other in positive context. So roughly that's the point. Mm-hmm. If this is what we mean by hyperintentionality, then there are plenty of hyperintentional logics in the literature, starting with Nelson's logics, of course. And all logics with strong negation are hyperintentional in this case. So that's very roughly.
Stanislav, may I also ask something?
Sure, sure.
Yeah. Look, your two axioms for an QN circle, right? Introduction, elimination of double negation, right? They make negation look classical, right? But in your motivating part, at least you somehow explained this whole problem.
No, it will not be classical, right? You don't have excluded middle, for instance.
Okay, okay.
And that ruins pretty much everything.
So what you told in motivating part about intuitionistic negative, it just preserved with these two axioms, right?
Well,
or not fully preserved.
This negation is a different kind of negation. It's a Routledge style negation. It's a kind of impossibility operator. Intuitionistic negation is a different thing. It's just phi implies bot.
Yeah, so in this logic, de facto, we have two kinds of negation.
Yeah, you have two kinds of negation. You can combine them in certain ways to get different kinds of necessity operations in particular. This has been done a lot in propositional setting. It has been done in quantified setting.
May I ask you a question on the same slide? So you claim that this insertion of this plus Qn gives basically hype, right?
Yeah.
But the problem is that, I mean, I think that we are scratching our head. It's that, so you said that this also gives constant domain, right? CD plus these things. But Hannes claims that hype is hype insertion of the the axiom of hype give already constant domain semantics, but it doesn't seem so. Have you had any problem in concerning this? It doesn't seem that Hannes axioms can prove constant domain semantics, or at least the axiom of constant domain semantics.
Well, he proves CD in his paper without giving much details, right?
Yes, actually, we are convinced that it's not possible, but so I was wondering if you had any...
I don't know how it might be not possible. I mean, the original axiomatization he starts with is essentially just positive intuitionistic logic.
Yes.
Well, maybe he missed something there, but it's definitely what he wanted to start with.
Yeah, absolutely, yes.
And once you have that and additional axioms like these two, then you'll be able to derive everything in the usual way.
Okay.
So if something cannot be obtained, then maybe the formulation is a bit tricky because he doesn't use two Bernoulli's rules, right?
Yes, exactly.
He used generalization and two more specific quantified axioms, which are usually known to be equivalent, but I think that they're messy, so I didn't go too much.
That's exactly my worry, and the other worry that I have is that so with this formulation you basically have exchangeability of equivalence for free, right? Or do you have to implement?
Yes,
you
have that.
You have that. You don't have to presuppose that, right? You don't have to have them as
sure.
Okay, because it seems that instead to fix Hannes' system for constant domain semantics, you have to have them as an additional rule. So it seems that it's kind of
I mean, everything will be as usual except for this modal negation. But for the modal negation, you will just use the contraposition rule to exchange equivalent formulas.
I see. Okay. Thank you.
Okay, so I shall henceforth often write this not phi, but this is a different kind of negation. For phi implies but. So this is our intuitionistic negation now. It's just for brevity. It's just an abbreviation, nothing more. So now we have two kinds of negation. We have a modal negation and this intuitionistic negation. Now, in the last section, what I wanted to talk about is I want to say a few words on the constructive properties of disjunction and the existential quantifier, right? So whether or not they behave constructively in hype or in Qn star or in Qn sharp. So in other words, whether or not these logics have the disjunction property or the existential property. And the brief answer is no way. And it is so simple to prove that I will provide all the proofs in this section, right? So unlike with the completeness results, you don't need much to understand that. Now, in his work, Leitgeb mistakenly claimed that hype has the disjunction property. So he tried to use the same argument as for intuitionistic logic. So you have two counter models for phi and psi, and then you build yet another model such that if you go this way, then you falsify phi. If you go that way, you will falsify psi, and hence the disjunction is not valid. So roughly that's the point. Well, the construction of that bigger model is not correct, so the argument is flawed. But it requires a little bit more work to understand why it cannot be fixed. So in fact, it was observed by a former student of Sergei Odintsov, Sergei Drobashevich, that n star, and hence its quantified version, doesn't have the disjunction property because this very specific formula belongs to n star, but neither of its disjuncts does. So this looks as a really peculiar example. So I'm going to provide a very simple counterexample, which will work for n star and for all its extensions, including hype. So here is this example roughly. So consider the following scheme. I'm going to denote it by WEM, which stands for weak excluded middle. Well, just for me, that's weak excluded middle. It's a local name, right? It says that it is impossible that phi, or it is impossible that not phi, where not is intuitionistic negation. So it turns out that this thing, this schema, is derivable in Qn star. And since it already looks as excluded middle, then the disjunction property will fail, of course. So let me give some details. So why it is true? So first of all, consider this formula. Phi not phi implies this thing. It is derivable even in positive intuitionistic logic, because what you have here is that phi and phi implies bot, then something implies bot. Well, that's definitely even in positive intuitionistic logic, if you will substitute bot instead of one of the formulas. Now, then you apply contraposition and you will end up with this. And the antecedent of this implication is one of the axioms in n star. So you say not top implies bot. So this thing goes away and you end up with this formula. And then you apply one of the De Morgan laws, which is available in n star, and you get this formula. So it shows you at once not only that the disjunction property will probably fail, but also a kind of negation, negative disjunction property will also fail. So if you prove that thing, it doesn't mean that you will prove one of the negations here, right? So it's a bit stronger. And the argument doesn't involve any quantifier axioms or rules, so it's a purely propositional reason we have here. So now, in order to make things precise, let me introduce a notion of subclassical. So I will call a logic, a QN star extension, subclassical if it is a subset of predicate classical logic, right? So the maximum logic we may have here is predicate classical logic. And the corollary is that no subclassical QN star extension has the disjunction property. So why it is the case? Because suppose that we have a subclassical QN star extension. Since it's subclassical, then there is a formula, some very simple formula, such that neither of these two is in L. So you take just something very, very simple. If you think of propositional logic, then not P and not P will suffice. Of course, neither of them is in your logic, right? Because in the classical context, these two negations is just the same negation, right? So this is just phi, essentially. Now, this thing is not in your logic. This thing is also not in your logic because they're not in classical logic. But the disjunction is in your logic because we proved that. It is in QN star, so it's in any QN star extension. And that's all. So the disjunction property fails. And it's easy to see that QN star, QN sharp, and Q hype are all subclassical. Hence, none of them has the disjunction property. Well, and of course, the same applies to their propositional versions because we haven't employed axioms at all, quantifier axioms at all. Okay, now this is about the disjunction property. I'm going to say something on the existential property, which essentially generalizes the disjunction property. So if the disjunction property fails, then the existential property is expected to fail. So how to prove that? Formally, now the existential property is a bit more tricky. I will assume for simplicity that our signature includes exactly two constant symbols, say 0 and 1. It's not really important. Maybe you have a lot of them, but similar argument will suffice. Now consider the following schema, WCP, where WCP stands for weak choice principle. Don't really think about it. I mean, it's not really a choice principle, right? But still, what it says is that if this thing is not true, roughly, then by weak excluded middle, you can erase this thing. Then one of these negations will be true, and then there exists X such that not phi. So that's a very simple reasoning. And I say that this thing is derivable in QN star. Well, here's an informal argument which can be easily turned into a formal derivation. So if this thing is true, then the whole disjunction is true. So we don't care about that. Suppose that this thing is not true. So not this. Then by weak excluded middle, we have the impossibility of this conjunction. So we just erase this intuitionistic implication. So if this thing is not true, then it is impossible, then phi. Okay, now by one of the De Morgan laws, the one which is available in N star, we can write this disjunction. Now it means that it is impossible that phi of 0, or it is impossible that phi of 1, then there exists X such that phi is impossible, right? So that's very easy. Okay, now we have this weak choice principle, and it turns out that no subclassical QN star extension has the existential property because of this principle. So let us show that. So suppose that L is a subclassical Qn star extension. Now, evidently, there is a formula Q phi of x. We'll say, think of pi of x, where pi is a unary predicate symbol, such that neither of these formulas is in L. Well, you can make this thing true, then the whole thing is false, and this thing, you can make it false, then the conjunction is false. And two negations, we don't care about two negations if these are classical negations. So even in classical logic, it is not the case. Now, on the other hand, in intuitionistic logic, you can do this trick. So if x is not free in psi, then from psi or there exists x theta, you can derive there exists x such that this disjunction. So what it means is that here you can put this existential quantifier in the front and end up with this formula. Now it belongs to L, which means that its substitutional instance must belong to N, to L if the logic has the existential property. But the only two terms, I mean closed terms we have is 0 and 1, and neither of them work. So that's the end of story. So what it means is that in particular, none of these logics has the existential property. So you may not hope for any constructive properties of negation here. Of course, for intuitionistic negation, you will have some properties, right? Now, this is pretty much it. But let me say a few words on some directions that might profitably, hopefully, be explored. Now, first is that since N plays an important role in studying propositional intuitionistic model logics, at least this is something Dawson started with. It might be interesting to investigate predicate versions of such logics, of intuitionistic model logics. The second direction is that it might be reasonable to develop predicate versions of the logics presented by Liddick and Visser. So they have very similar kind of semantics. So probably the same technique will apply. Still, they have a new conditional, this strict conditional, which is binary, so that there might be some surprises, of course. Now, third, it might be useful to introduce and study sequence systems for Qn and its extensions because it should help us to analyze interpolation and certain other mathematical properties. And it's not clear whether or not these logics have. And finally, we could try to employ Qn star extensions, or rather Qn sharp extensions, to provide a framework for studying first order logic programs with negation, not propositional logic programs with negation, but first order logic programs with negation. So developing some well-founded semantics for first order logic programs and understanding what happens there. So roughly the motivation for the logic N star was the following. In classical logic programming, if you have a program without negations, then its meaning is completely determined by the least fixed point model. Now, if you have programs with negation, then the situation changes and there are different alternative semantics. But for all of these semantics, there is no unique, well, usually there is no unique nice model. Rather, there is a collection of minimal models. For instance, in answer set programming. So you have a program and you have a collection of minimal models for that program. In this way, logic programs with negations, they correspond to certain NP-complete problems. So this is very roughly speaking. So this is why this is a new paradigm in logic programming, roughly. So it is closely related to complexity theory. And people like Gelfond and Lifshitz have investigated that quite a lot. Still, the problem, I mean, the main concern of this enterprise is that sometimes you want to modify your programs. You want to take a subprogram of a given program and then replace it by a different yet equivalent program. Now, okay, but in order to do that, you need to know that these programs are somehow equivalent. What it means equivalent, it means that they have the same well-founded, stable, or whatever models. But that's very problematic because the semantics is, the underlying logic is non-monotone. And the motivation for Kabbalar, Odintsov, and Peirce was to find some nice monotone logics such that they correspond directly to this equivalence of programs. So programs can be replaced by each other if and only if they're equivalent in this monotone, nice, decidable logic. So, and they found such logics, and all of them somehow extend n star. So that's roughly the story. Also, I would like to mention some technical aspect of the strong completeness result for QN sharp and hype, because I think that it is interesting. Well, at least I don't know what to do with that, right? I mean, maybe I'm just too stupid, but so here's the thing. If we're concerned with constant domain models, as in the cases of QN sharp or Q hype or CD, or I don't know, the quantified version of the logic K over constant domains, a rather specific kind of extension lemma is needed. So this is called Creswell's lemma. Well, at least this name has been suggested to me by Valentin Schechtman, because as far as I understand, this lemma first appeared in an introduction to model logic by Creswell. And as far as I remember, it was then adapted to predicate intuitionistic logic by Skvortsov. So this is a rather specific lemma because its proof, at least the version I found in the book Quantification and Non-Classical Logic, doesn't generalize readily to uncountable signatures. So you start with a certain very nice theory, and then you extend it in such a way that at each step you have added only finitely many formulas, and that's very important, right? So when you reach step omega, the construction will not go further. It's not clear how to carry it above omega. Of course, we can still obtain weak completeness results using this technique for arbitrary signatures, because you can always, restrict your attention to the symbols that appear in your formula, but then we need other ways of proving compactness. And you need alternative ways of proving compactness, not via proving the strong completeness result, but you need separately to have compactness and this thing. And at least as far as I know, there are not so many general techniques for doing that. So, of course, in some books you will find these examples. If you take a look at Introduction to Proof Theory by Sam Buss, then you'll see that he proves weak completeness for classical logic at the very beginning, and then he says we also have compactness theorem because, ultrafilters and things like that. But this is a very special thing for classical predicate logic, right? In the case of propositional classical logic, you will employ Tikhonov theorem, for instance. But that's also rather specific. What you want to have is a general technique of showing compactness, not via strong completeness, but in some other way, right? Then you can combine these two. You may have a nice sequent calculus, which will suffice to prove weak completeness, and then you need to have compactness. Compactness plus weak completeness equals strong completeness. Now you're done. Okay. Finally, let me just mention a few papers. So there are some references, further references, more references. So the first one is just my manuscript, which has been submitted recently to RSL. Probably I will upload it to archive at some point. What happens here is essentially a quantified version of what happens here, even though I haven't seen this manuscript when I wrote my own manuscript, but it appears to be so, right? This thing is also submitted. And probably it's already on archive. Here's one of the Dawson's papers, the paper where the logic N was introduced. Here's a paper by Routley. Here's a paper by Kabbalar, Odintsov, and Pierce, where they motivate N star by some considerations and logical foundations of well-founded semantics or logic programs with negation. A more technical version of what happens here is a paper by Odintsov. The logic hype, the propositional version of it, seemed to be introduced here by Moisel in 1942, but again, I haven't seen this paper. I have no idea where to find it. I only was said that it is definitely there. Okay. The quantified version, of course, appears here with all the proofs and all the flaws, but still, I mean, that's 19 pages of some very interesting reading on what happens in this logic, and with a lot of references and an extensive bibliography. Now, if you want to do some quantified non-classical logic, you need to have a good source for the techniques involved. So that's probably the book I would recommend. The canonical model construction appears on page 500 something. So you need, so sometimes you really need to go into details, but on the other hand, of course, books like Creswell's Introduction to Modal Logics are good from a philosophical perspective, but if you really want to understand some details, you need to have a good mathematical book. Here's where you can find Vakarel's thoughts on his classification of negations. Here's one of the papers by Sergei Drobishevich. Actually, his PhD thesis was devoted to N star, so he knows quite a lot about this logic. And here's a paper by Liddick and Visser that I mentioned previously. That's pretty much it. I hope it wasn't too boring. Thank you very much for your attention.
Very nice, thank you. Okay, so does anyone have questions? I have some, but I would like to first let other people ask.
May I ask something?
Yes,
I have actually two questions. The first one is, what happens if you drop constant domain axiom? So does it make sense to deal without it?
You mean here?
Yes, here. Yes, you have it explicitly as one of the axioms. Yes, without this one.
Well, it's not really clear what is going to happen. So it's clear that if you have these two axioms, then you would like to have constant domain requirement with respect to the accessibility relation. But maybe not with respect to the information ordering. So CD is responsible for constant domains with respect to the information ordering.
Yes.
But on the other hand, they are already very tightly related in the semantics because, well, from the very beginning, we have some conditions that relate them. And in Routley style semantics, they are also, of course, related because the star operation is anti-monotone function. It means anti-monotone with respect to the information ordering. So if you're going to only require that you have constant domains with respect to the accessibility relation, but maybe not with respect to the information ordering, I think that something will go terribly wrong at some point in the canonical model construction. But of course, one can try to do that. I know that this works, and I haven't managed to make it work without it. Right. So then
I see. Yes, because intuitively it is not intuition. It contradicts intuitionistic principles. Basically, this CD. Well, it was trying anyway.
As well as N1 and N2.
Yes.
I mean,
N1 and 2 are yes.
N2 at least.
N2 is not very intuitionistic. Yes. Yes.
It's more, it's similar to Markov's principle, right? So this
yeah, but constant domain is something else. Yeah. Okay, but this is worth trying to see what happens. Yes. I haven't got another question. It seems that many years ago I heard this question from somebody, maybe from some Bulgarian logicians. So what if you consider double negation as a model operator? Forget about single negation. Do everything with the double negation. So this looks nice from the viewpoint that you have monotonicity now, and maybe some other things get nicer and simpler. Did you think about this?
Well, I think that these things, well, at least that's what I would expect. I haven't looked to details, but I think that quite a lot of work has been done on combining different and probably the same kinds of negation, and thinking of them as a necessity operation. So here's just one example where composition of intuitionistic negation and negative modalities was considered as a necessity operator. And there is a whole theory of classification of what we may have there. So roughly the point is that people combine different kinds of negation, think of them as a positive or negative necessity operator, as a positive or negative model operator, and then trying to axiomatize it in its own right. So forgetting about that we had two negations in the first place, now we have their combination, and trying to understand how to axiomatize it, right? So perhaps it satisfies monotonicity rule, but maybe it satisfies something else. What exactly, how to do that? Can we prove strong conflict?
May I ask a more specific question to this point? So exactly, so that was one of my questions too. So suppose you, well, can you enrich the language of your logic by a positive model operation box and define your negation as box phi implies bottom? Would that be
as
so?
box?
Sort of you interpret your negation here as a combination of let's say necessity unknown to us and the usual intuitionistic negation. Would that be
well? Of course, you can do that in a superficial way. So if your implies is material implication, just material implication, like in K, right? And if your box is related to the same accessibility relation, then this is exactly it.
So you need another implication then. What I meant was to have the original intuitionistic implication. So box phi implies bottom, where implies means the usual arrow.
Yes, so you have classical, so where is the semantics? Okay, so the negation here in this original logic just means that for every world are accessible from a given world, it is not true that. So if you have material implication And if your model operator corresponds to the same accessibility relation, this is exactly it. But this is not intuitionistic implication anymore, right? So now you have material conditional on the top of it. It's not clear what will happen if you have the original implication there.
Okay.
Well, it can concern Valentin's question. I think that this is something that I found very much surprising, because in the these axioms, I mean, the analogs of these axioms, they also appear, I mean, N1 sharp and N2 sharp. They also appear when you consider Nelson's logics with strong negation. And the way you think of them is that these are just generalizations of De Morgan laws. But De Morgan laws in here, in the logic Q and star, you also have all the De Morgan laws, but they do not force you to have constant domain semantics. Now, when you add the quantified versions of these De Morgan laws, they somehow force you to have constant domain semantics, and that's rather specific. And it's not clear how to prove the strong completeness result unless you also add CD on the top and then work with constant domains. But then you need a different kind of extension lemma. Instead of prime theories, you have some AE prime theories. So it's something stronger, actually. Otherwise, the construction will not go through. So you have to modify a lot. And that seems pretty strange to me. But yeah.
I have a thinker on that.
Yeah.
So on this question of the constant domain semantics, so apparently, if you make the existential intentional in a way, so if you think of the for all quantifier, usually in the intuitionistic predicate logic, we take the for all to be the intentional one, like in the sense of that it looks at all the possible words. If you take also the existential to be intentional, then you lose basically the dual of the constant domain semantics. But apparently, you get a theory which is kind of nice. So it's something that Martin Fisher is working on right now, and on the background of hype and other stuff. But apparently, so if you drop not only CD but also, so it would be phi and phi and exists x psi not exist x, so phi implies exist x not blah blah blah. Then you have something which apparently is nice. So maybe something to.
Well, maybe. So I mean, well, one of the problems I had is that, of course, I wanted to start with Routley style semantics at some point. And if you start with Routley style semantics, then you're wondering what is the logic of Routley frames with extended domains rather than with constant domains. And that's not clear.
Yeah, definitely.
Okay, may I ask yet another question? So
yeah, okay.
So what is the real advantage of this Routley star semantics compared to the usual Kripke style semantic that you started with? So the special models or whatever. So you said somehow that the star is good, but that I didn't understand. Why exactly is it better than Kripke? Kripke is more general, more familiar, and somehow the conditions that you have there also look sort of simple.
Oh, you mean these conditions, like that one?
Yes.
Well, it's well, it looks simple on the technical side, of course, but it's not that intuitive, of course. So if you have an anti-monotone operator that corresponds directly to the behavior of your negative model operator, then it's somehow easier and nicer to deal with that. But I also think that one of the reasons is because Routley style semantics has become very popular in irrelevant logics as far as negation is concerned. So
Okay.
it suffices for them.
Okay. So if you are, so if you go from Kripke model to Routley star model, how complicated is this move? So by canonical model, so how does it work technically? So you first have this canonical model, which as expected should be something like a relational structure, but then you modify it to get this star function, or does it work some other way?
There are a lot of details here, of course, but roughly, of course, you need to define a star operation nicely on your prime models.
Mm-hmm.
So that each prime model, each prime theory will be mapped to a star theory, which is also prime, and everything is nice and good.
So you define this star operation directly on the canonical structure?
Yeah, sure.
Okay.
But the point is that it's very it turns out to be practically impossible to define it here, for instance, in Qn star. So in the propositional version, this semantics with respect to special frames is equivalent to a Routley style semantics. So you don't need to add these generalized De Morgan laws for quantifiers. Everything works, the semantics is equivalent. But if you try to generalize it to quantifiers, then at some point you define for each prime theory gamma, a theory gamma prime, and you cannot prove that this new theory is again prime and nice and good and so on, without using generalized De Morgan laws. So that's where they appear. Okay. And now you can see that if you want to have a nice Routley style semantics, you need to add these two. On the other hand, a strange thing happens, I think, also here in QN circle, because here you don't even have CD. So the only thing that you have is quantified positive intuitionistic logic, and you have double negation introduction and double negation elimination. But using them, you can derive all the De Morgan laws, these generalized De Morgan laws, and also CD. So it's not clear, I mean, where is constant domain requirement here? It's just double negation introduction and elimination. It says nothing about quantifiers. But using Bernoulli's rules and everything, you'll be able to get that. So it seems to be inevitable, at least in hype. So it seems inevitable that you'll have to stick to constant domain semantics here, because of double negation introduction and elimination, not because of something that is related to quantifiers. You have the usual axioms for quantifiers, just like in intuitionistic logic. There is nothing there that tells you that your domains are constant.
Okay. Any other questions or remarks? So what was the reaction of Lightgood to all this? That was.
Well, I think that it is. Your question is mostly concerned not with my paper, but with this paper, because they sent this paper before me. I mean, criticizing some of his philosophical claims about hyperintentionality. So you should better ask Sergei Odintsov. Probably he knows a lot about that, or Heinrich Wanzek.
No, my question was actually slightly different. So there is this nicer semantics for his system, which apparently works better and somehow is simpler, etc. So what was his reaction to that? Did he liked it or what?
Well, actually, I haven't asked him. Well, I think that he should like it, of course. I mean, but the problem is also
that would be my expectation, actually.
But also, as Elio mentioned, there are some questions concerning his original formulation of the calculus. It's not clear, either he forgot to include something in the original calculus, or actually some peculiarities that seem to arise there are like internal to the system. Because he uses a specific formulation of, well, not a very specific one. So he uses a formulation of positive intuitionistic logic that is close to the formulation that you will find in the book by Shechtman, Gabay, and Skvortsov. And in this formulation, you use a generalization rule instead of two Bernoulli rules, and some specific quantifier axioms. It's not clear whether the calculus he started with is really equivalent to the one where you have two Bernoulli rules and two quantified rules, as I have. But it will be very strange if they're not equivalent anyway. So you start with positive intuitionistic logic anyway. The construction shouldn't depend on what formulation you have at the very beginning, and then add the contraposition rule and everything.
Yes, maybe it would be nice if we could talk about this, but just wanted to add like a little remark on maybe why the semantics is so complicated in the case of hype. Well, first, I think that there are some case studies that he makes that like require the semantics, or the so-called full model or hype full models that are kind of interesting, I guess, for some applications. Apparently, there is this application with graphs, and so for that you kind of need some kind of more modularity, I guess. And the other thing would be interesting to see if this alternative semantics, how it would apply to this modal logics that Hannes is developing. Unfortunately, there is nothing out yet. I could see a presentation, but there and to create this hyper-intentional context, as he calls him, like for things as Y and different kind of model operators, then you really need some kind of modularity and some kind of like interrelations between the fusion of the states and these compatibility relations that seem very fine-grained. But it would be nice to see if this can be replicated into your setting.
Well, I mean, I think that one of my concerns is that the only real application he provides in his paper of 90 pages is that application to theories of truth. And the intended model he provides there, I mean, it can be easily translated into a Routley style model. So there is nothing there. You don't need this difficult kind of semantics. You have a star operations there explicitly in his model. So at least that application translates into this semantics easily. You don't need all those complications that come on the first 20 pages. Maybe there are some other things in the middle that will require that, but that's a different story. He still says that with an application to semantic paradoxes. So that application does need
absolutely.
That. Okay.
Absolutely. Yes. No, that's for sure. Yeah.
Okay. So that was a very nice and interesting talk.
One more question. Well,
yes.
Maybe a bit technical. So as here the negation is sort of a modality, I think it suggests that it is in a sense non-canonical. So even if it is, you say you have two operations axiomatized by the same set of rules and axioms, and they could be non-equivalent in a sense. So does it make sense to consider polymodal versions of this stuff?
Well, yes, it should be non-canonical in the sense that, yeah, they will not be equivalent. But the same applies to, I don't know, Nelson's logics. So if you have two strong negations, they will not be equivalent, or something like that, even if they satisfy the same set of rules. I'm not sure about that. Well, at least no one considered polymodal versions of Nelson's logics with strong negation, like two strong negations and things like that. So I'm not sure how to motivate that in this context. But
my interest to this comes from these sub-exponentials in linear logic. So it's absolutely different. There's also something which is a modality, and it's the only thing in linear logic which happened to be non-canonical. And then people just came into it and started considering these logics just from bare interest, and now they have some applications. They're in, I don't know, formal verification, stuff like that. So this is why I wondered whether it could make sense here. So it's purely propositional and quite general, so it's also applicable to Nelson logic, and I think to many other logics of similar sort, but maybe it could make sense.
Well, maybe, but I mean, if you just consider a polymodal version of this logic, I think that that the method will probably apply, because also in the book Quantification and Non-Classical Logic, as far as I remember, only only logics with one model operator are considered. But I think that a lot of what is said there will generalize readily to polymodal versions. So, but on the other hand, logics will become increasingly difficult to handle, because, well, even in propositional logic, I mean, there's a huge difference between K and K fusion K. There is also a huge difference between S4 and S4 fusion S4, right? For S4, you can investigate some general properties like interpolation from an algebraic perspective. And it's not clear what is happening with S4, fusion S4. Probably K is already there. And I mean, the whole class of extensions, and then everything is bad, and so on and so forth. But that's maybe just not the right way of thinking about it.
Well, in our book, we formally defined everything for polymodal case. But
okay.
But there was nothing specific for polymodal case. Yes.
Yeah, to consider 5 different negations simultaneously is a good idea, I think. we can yeah, specify our level of negating very distinctly using 5 different modes of
sub-negations in a sense.
Yes. Yeah, okay.